Hey everyone, welcome to problem 2.31 of David Griffiths Electrodynamics. Alright, so this problem states that we have three charges situated at the corners of a square, and each side has a length A, as shown in this figure that I've drawn here. It asks, part A at least asks, there's two parts here. How much work does it take to bring in another charge plus Q from far away and place it in the fourth corner? So I've labeled the corners 1, 2, 3 here, and then the fourth corner is this one up here. Oops, I was on erase mode. Yeah, that works, whatever. So, and in corner 1 we have a charge of minus Q, corner 2 we have a charge of plus Q, and corner 3 we have a charge of minus Q. And the fourth charge will be a positive charge plus Q, bringing in. So, real quick, if we have a collection of point charges, the potential created at some point in space is just given by this equation here, 1 over 4 pi epsilon naught, the sum of all the charges over all the charges and the distances between the charges and the point in space at interest. And we can sort of use this equation to develop, you might have just saw the lightning there, it's storming outside, but we can use this equation to sort of calculate what the work would be to bring in this fourth charge. So real quick, if we were to bring in a charge Q here, well, this charge, charge 1, is going to, produces a potential, and it's going to also, if we were to bring a charge here, it would produce a force on this charge. But more importantly, we're talking about potentials, so it would produce a potential at this point. The potential at this point that this charge creates is 1 over 4 pi epsilon naught, minus Q, since this is a negative charge, divided by the distance between this charge and the potential point, which would be the length of the square side, which is A. And so that's what this first term is, and the summation. Okay, I've just sort of wrapped the summations of all three charges into one, because they factored out the common factors. That's what this first term is. The second term is for this bottom charge. So this charge also produces a potential at this point here, and we can do this because of the principle of superposition, if you guys remember. But the term here is going to be exactly the same, 1 over 4 pi epsilon naught, positive Q, since this is a positive charge, divided by the distance from this charge to the potential point, which is this R term here. And that distance is going to be the diagonal distance across, which you can find by recognizing that this is a right triangle here. If you draw that line across, and then you have a right triangle of two sides are length A, so that would make, using the Pythagorean theorem, this side root 2A, and that's that second term. And then the third term is this third charge down here, minus Q, and the distance between this charge and this charge is A. So that's how you get the potential, and when you factor everything out, you get Q over 4 pi epsilon naught A times -1 plus 1 over root 2 minus 1. And then you can combine the negative ones and you get the same thing, Q over 4 pi epsilon naught A, -2 plus 1 over root 2. So that's the potential, the total potential that the collection of these three charges make at this point in space. So if you want to find the work done to bring in another charge plus Q, then the work is just where I labeled the work sub 4 is the work done to bring in that fourth charge, is the charge of that fourth charge times the potential, which is, so QV, and so it would just be Q squared over 4 pi epsilon naught A times -2 plus 1 over root 2, and that would be the work to bring in that fourth charge. So now to part B. Part B says, how much work does it take to assemble the whole configuration of four charges? So not how much, what we just did was calculate the work done to assemble that last charge, the work for the fourth charge, but how much work does it take to assemble the whole configuration? So that means we need to calculate the work to bring in the first charge, the second charge, the third charge, and then lastly we can add on the work for the fourth charge, which we already have. All right, so the work to bring in the first charge, well, if this is a situation where there's no other charges in existence at this point in time, so the work to bring in the first charge, well, is 0 because there's no other charges acting on that first charge to bring in. So there is no potential and there is no work to bring it in. It just freely comes in. So that makes the first one easy. So what's the work to bring in the second charge? Let me condense that. The work to bring in the second charge would be plus Q, because the second charge in the bottom left corner is positive Q, times the potential created by the first charge. V1 is what I've named it. Which the potential created by one point charge is the charge negative Q in this case, divided by 4 pi epsilon naught and the distance to that point, which is A. And so the work done is just that, you take positive Q is the charge of the second charge we're bringing in, multiply that by the potential, and you get minus Q squared over 4 pi epsilon naught A. And that's what it takes to bring in those first two charges over here. That's the total amount of work it takes. Now, the work of the third charge, well, now we already have two charges in place, so that third charge is going to have to act against the already existing two charges. There's already a potential created by those two charges in place. So it'll be negative Q, because the third charge is negative Q, has a charge of negative Q, times the potential V12, which is just the potential of the existing two charges already, which would be this up here. Anyways, so I wrote the negative Q out, and we multiply that by the potential created by the first charge, right? So to bring in, to bring in a charge here, well, the first charge creates a potential here of negative Q over 4 pi epsilon naught times the square root of 2a, because the distance between this is the same as that diagonal distance, and so it's still root 2a. So that's what that first term is here, plus the potential created by this bottom one here, and that's the same, plus Q over 4 pi epsilon naught times the distance between that, which is a. And that's what this is. And then you factor out those terms, common terms, and you get, it looks like I didn't factor it out here, but if you factor it out, you get Q squared over 4 pi epsilon naught a, 1 over root 2 minus 1. Or you can keep it in this form, which for some reason I did. So that's the work to bring in the third charge. Now the work to bring in the fourth charge, I guess I decided when I was doing this problem to just do it all over again, but this is exactly what we calculated in part A. This is exactly what we found in part A. So there's no need to do this again if you need to just look at part A to figure out how you calculate the work to bring in the fourth charge. So the total work to assemble all four charges in this configuration would be to add up all the work that it takes to bring in each charge. So that would be the work to bring in the first charge plus the work to bring in the second charge plus the third charge and plus the fourth charge. So you add all that up, which I've shown here, the total work. And that would just be 0, which is work 1, plus negative Q squared over 4 pi epsilon a, plus Q squared over 4 pi epsilon a times 1 over 2 minus 1, and plus the last term, which is Q squared over 4 pi epsilon a times the 1 over the square root of 2 minus 2. And you can do some factoring here and combine like terms. So obviously we can factor out the Q squared over 4 pi epsilon a as a common factor. Then you're just left with minus 1 plus 1 over root 2 minus 1 plus 1 over root 2 minus 2. Combine all of that again, everything in here, you get Q squared over 4 pi epsilon a times minus 4 plus 2 over root 2. And then you can factor out a factor of 2 to get 2Q squared over 4 pi epsilon a times negative 2 plus 1 over root 2. And this is probably the simplest form you could get it in. You can cancel the 2 if you want. It's whatever you want to do at this point. But yeah, that's pretty much it. This is a pretty simple problem. Not much to it. So if you guys have any questions and you need some clarification, please feel free to let me know. And if you guys want to support the channel and get access to the PDF solutions of these problems, you can subscribe to the Patreon account, which is linked down link down below. And yeah, thank you guys for watching. Always appreciated, and I hope you guys have a great day.